Okay, so we may be better now. That's interesting. We have an old beamer here, a projector. So this was the last slide yesterday. And so in the following, I would just like to give you some brief ideas about research in this area of CMOS or semiconductor MEMS that we did at our chair. And then I will go into the chapter 2. Yeah, so don't expect me to explain all the details of this summary slide set. So let me go right away to the first. So one of the developments in my chair is about magnetic sensors. There will be one chapter dedicated to magnetic sensors based on CMOS technology. And you see here a little microscope, an optical micrograph, a microscope image from an optical microscope, where you see an interesting structure. Yeah, it's a structure with 5 contacts. Yeah, so this is viewed from top, 5 contacts contacting an N-well. Yeah, the concept of N-well you will see in chapter 2. And that doesn't look like a Hall sensor, yeah, because a Hall sensor usually is a square thing or a symmetric thing with 4 contacts. And here we have them all aligned. Yeah, so this is a very particular kind of Hall sensor that is able to measure the B field component, the magnetic field component in the plane of the chip. Yeah? Whereas the standard Hall sensor, these Hall plates measure the magnetic field out of the plane of the chip. Yeah? So by making this development or basing our work on this kind of structures and making them better, we have enabled Micronas, a company here in Freiburg, to make better 3D magnetic sensors. Yeah? So they've patented an idea, and they're benefiting of that patent and producing these sensors by the hundreds of millions. Yeah? I'm very happy to know that our academic work, is useful in the industry. And apart from that, of course, we work also on the deep understanding. I mean, improvements always are based on deeply understanding what happens. Yeah? And so you see here a slide that I will explain in chapter 3. About some interesting symmetry properties of general objects with 4 contacts. We call that reciprocity theorems, and they're extremely useful. And they reflect some deeper insight or deeper symmetry of phenomena, which you can only grasp if you know the physics underlying these phenomena. And I will explain that in detail. It has fantastic implications about compensating effects that are also playing in these devices that disturb your resolution or your accuracy rather, and by these insights you can develop simple methods to compensate for these undesired things. So I'll skip that. Then here you see an example of a tactile sensor. This tactile instrument has a little tip. The chip is 6 by 6 millimeters, and it is a micro machine structure actually, so a cross bridge. And so whenever this tip contacts a surface while scanning a surface, you detect that by an ever so tiny displacement of the structure, deformation of the structure, and that deformation is measured using piezoresistive sensors. And the structure has also been, well, this one has not been fabricated in CMOS technology, but in our clean room, but we have also a CMOS version of this with integrated circuitry on top. So it's an extremely precise instrument with which you can scan the surfaces of micro parts. This little tip is only 100 micrometers around. It's a diamond or a similar ball sphere, and you can then scan over the surface with an accuracy of 10 nanometers. Yeah, and those 10 nanometers are 3D coordinates. So it's a very, very precise tactile instrument, much more precise than the DECTAC or so that you may have seen in the clean room. I can only measure essentially flat profiles, steps. And so one PhD student also worked on high pressure sensors for pressures up to 600 bar based on some glass and silicon component. The silicon part up here is also a CMOS part. It's fabricated at Micronas actually also in this case. And we have a piezoresistive element that beautifully transduces this external, the deformation caused by the external pressure on this compound structure. The glass has a different elastic modulus than the silicon, so it contracts more than the silicon. The silicon bends, and that exerts some mechanical stress. And that mechanical stress is then modulated by the fact that we have micro machine cavities here, or slots, trenches. And so there is a uniaxial stress that can be measured with this piezoresistive element. Piezoresistance is the subject of, or mechanical sensors is the subject of chapter 4 then. Here is another impressive example that was elaborated by Benjamin Lemke, another PhD student of mine, in collaboration with Intel. Yeah, so you probably have heard the slogan "Intel inside." Yeah, I would say inside Intel. Yeah, because we had a project with them, and this shows you how these big processor chips are built. I mean, they have all this logic, all these trillions of transistors implemented on their surface, but then there are these metallization layers, and then there's the packaging around that through which the contacts need to reach the outside world. Yeah? And this package has actually hundreds, if not thousands, of contact points, little contacts that are then contacting some substrate, which reroutes these hundreds or thousands of signal paths to the outside world. It's not just one line through which all the information passes, and then beside the drive voltage of the chip, that wouldn't be efficient. There are hundreds and thousands of lines through which information passes to be distributed to other components of the system. And this chip is large. It's the largest one that we ever made. 8 and some millimeters long and 3 roughly millimeters wide. And if you look below, there is a lot of microelectronics, switches and contact pads, of course, and protections for the voltages, contact pad protected pads, and then you have also sensor arrays actually. So many mechanical sensors in an array, 10 by 10 or 12 by 12 or 7 by 7, depending on the manufacturer or on the purpose. And they lie below some of those pads. Yeah, if we look at this location here, yeah, we have an array just below. Yeah. So when this chip is packaged and the packaging pulls on the system and threatens to destroy the interfaces because of shear stress, we are able to measure those shear stresses in situ. So this was a chip that was developed in collaboration with Intel for the purpose of, first of all, knowing the mechanical constraints in packaged big chips and for improving the packaging technologies. Yeah, then here is another subject, intracortical probes for neuroscience. That's also a big area in my group. Actually, Dr. Ute is leading that with much success, many European and other projects. And what you see here, I would say, well, so the purpose is to interface to the brain. Now, this is a human brain, and this kind of structures already exists. Deep brain probes do exist to treat diseases like Parkinson. It's shaking that elder people develop, tremor, as it is called in medicine. And there are so deep neural probes that reach the stem of the brain and there inject currents to calm that tremor. and allow people to live a better life, or we have surface cortical grids. And so these structure, when you look at them, are kind of rough. And these are big nails going into the ground. And the purpose of microtechnology is to make fine structure that make the best out of the space and information that is available. And so we have developed, let me just show here this example of a structure, probes with many different little electrodes that can, in a very detailed pattern, inject currents or extract signals from the brain. And this is made possible by CMOS technology, which allows to integrate microelectronic switches in the system to address these different electrodes. So there are 188 electrodes, many more than in these deep brain probes. They have 18. So you're very badly resolved in space. And with 188, of course, you learn much more about the brain. And these neural probes that you see here, either single shank probes or quadruple shank probes with the bases, have, well, this big thing has over 8 or close to 800 electrodes that can be, whose signals can be read out through these pads at the end. So, and here you see, for instance, one of those platinum electrodes that are integrated on these probes, contacted via these contact pads to the circuitry below. Yeah, there are also some probes with integrated light emitting diodes or laser diodes. And then we have some effort in the area of material characterization. Actually, that was my first experience with CMOS technology, apart from developing some sensors with PhD students, infrared sensors and gas flow sensors that are now in the product line of Sensoria. We developed, I developed, I strove myself as a postdoc to work towards characterizing the properties of these materials used in CMOS processes. Because if you want to design a sensor, you need to know what properties, quantitative properties you are benefiting of. And therefore you need to extract those properties. But it's not so easy. These materials are very small. If I give you a big chunk of materials and measure the thermal conductivity or the heat capacity or the thermoelectric power, that may be easy in a big chunk. But when you have a micrometer thin film, how do you do that? And so we had a whole range of methods to be invented to extract these properties. And what you see here actually is an interesting structure. That's a micromechanical structure that measures the property of this little bridge. So this is a 1 micron or half a micron thick bridge of silicon suspended between this frame and the surrounding chip. Everything was etched by deep reactive ion etching, except this little object. You see here these flat structures, vertical flat structures. These are spring, blade springs that allow this central object to be pulled in one direction, mechanically pulled, to load this structure, to expose it to a longitudinal uniaxial stress. So this is like the Hooke's experiment, where you have a beam that you pull in one direction. But at the same time, this structure is equipped with contacts. You see lots of contact pads from inside and outside, and this allows to measure the resistance of that structure. So this is a way to measure the piezo resistance of this material that was produced by that particular process. And the structure was invented by João Gaspar, a postdoc of mine, who was a gifted technologist and a fascinating material scientist. And it was a lot of fun to measure here even the nonlinear piezo resistance coefficients of silicon and other materials. So this is just an example, and of course these structures are produced on the wafer, as you see here. Many of those You see also structures oriented in different directions because piezoresistance depends on the direction. So it has a tensorial property because of piezoresistance because of its crystalline structure, and therefore we measure it in different directions. So let me make that small again. Make view graphs small again. Yeah, sounds like a political statement. Yeah, and then so there are other properties. So here I illustrated some mechanical properties, elastic properties, piezoresistance coefficients, fracture. You can also load these structures until fracture. Yeah, then you know about their robustness. And we have pursued this wafer level approach, but I also have a track history, a track record, as one says, in thermal characterization, thermal conductivity measurement, heat capacity measurement, Seebeck coefficient. And this was all done by integrated test structures. So, yeah, and then there was some work on micro energy harvesting, which I will skip now. Okay, I think that's enough for this first chapter, and so now we can talk about technology. So imagine that you are facing this opportunity to use a CMOS process for some mass product, as we discussed yesterday, to create a system that solves the problem. A thermal sensor, or a sensor to measure something. Now you dream of any signal that you would like to measure, and then we have a starting point. And then there will be a question that you will have to ask yourself: how do I transduce that information I'm trying to measure into something that is available at the end electronically? So if I'm measuring magnetic field, then I will immediately think of the Lorentz force acting on charge carriers. What is this called? The galvanomagnetic effect, the Hall effect, and then I have answered my first question. I will use the Hall effect as a transduction effect to transduce from the magnetic field to an electrical signal. If I would like to measure some acceleration, well, I could think of a mass spring system, mass attached somehow to the chip, and when the chip is moved, mass can't move because of its inertia so fast, and then there is some spring that is kind of loaded a bit, and then maybe how do I measure that spring deformation? Well, maybe using the piezoresistive effect. So the piezoresistive effect, in addition to this mechanical inertial effect, will be my transduction effect. And if you would like to absorb radiation, infrared radiation, for instance, how many people are in the room without a CMOS camera? Can I measure the heat of your faces, to determine whether we need some ventilation or not, for instance? Then an infrared sensor may do the job. And how do I transduce infrared radiation in an electronic signal? Well, infrared radiation carries energy. It might heat up an object. So I need a temperature sensor integrated to measure the temperature change, depending on whether something is coming or not. And then I have also a transduction effect, heat absorption, and then some mechanism of measuring temperatures. That might be a thermoelectric transduction or a thermal resistive transduction, the change of the resistance as a function of temperature, or other effects, or a deformation. Thermal changes cause deformation. Deformation can be sensed maybe capacitively. Okay, and I have another idea. So I have dreamed up of many transduction effects based on what I know, or what I think of, or what I dream of, and then so that's the first starting point. Then we need, of course, materials that are able to do that. Do we have materials in CMOS available that can do that? Is there a material that has the Hall effect? Yes, there is Yeah, so silicon does that job easily. Is there a spring material? Yes, silicon is a good spring material, but also the thin films are good spring materials. Yeah, so these are elastic materials, like silicon oxide, silicon nitride. So, or what about heat absorption? Yeah, some of those materials are transparent, but they absorb infrared. They are transparently visible, but they absorb the infrared radiation. Yeah? And so this question, which CMOS material is able to perform the transduction, is the next step. And it requires experience, but I think we will elaborate that know-how during the lecture. Yeah? Of course, other questions that need to be answered is it compatible with the condition to which it will be exposed? So in some cases, the answer is right out no. If people ask you to do some high temperature, harsh environment sensor in the oil drilling business, 3,000 meters below the surface of the earth, it's very hot down there. The CMOS chip will not survive for long. So the answer is we need totally different materials. And then if those materials are not available in silicon, in CMOS technology, then probably it's not going to work. Besides the fact that CMOS chip usually only work up to 150 degrees or 180, and then it's over for fundamental reasons. So if in other cases, no CMOS material can do the job, I had some typos there in the script I saw, so they are corrected here, so you may look it up. If no other CMOS material can do the job, maybe elaborating some other materials on top of the CMOS may enhance the CMOS part. That's a way. Yeah? So adding materials can be efficient, or removing materials can also be efficient to expose some properties that were not there before. So thermal insulation, for instance, in a thermal sensor, how do you achieve that? Silicon is a very good thermal conductor. So if you would like to heat up a spot on the chip with some incoming radiation, or with the chemical reaction energy of some volatile organic compound with some added material on the surface of the chip, and you would like to measure a temperature increase, if there is a silicon substrate that immediately removes that that heat quantity, there will be no temperature change. So what can you do? You can remove the silicon to keep only materials that are non-silicon, that are insulating, like silicon oxide, silicon nitride, maybe, maybe only the necessary metal structures that are necessary to bring in some, some current into some thermometer structure locally. But then you have a thermally insulated structure, a membrane or a bridge that can do the job. And many sensors, like thermal flow sensors, chemical sensors, radiation sensors, work exactly with that principle. On the fact that we know how to remove silicon from the chips. So that's it. And then of course it needs also to be everything. So this added material thing or the micro machining thing needs to be compatible with the CMOS technology. If you then invent a method that works at 1,000 degrees at the end of a CMOS process, then I'm sorry, the diffusion profiles are gone. Your transistors don't work anymore. So usually the added processes are at low temperatures. Then chemical compatibility needs to be studied also. KOH, etching is okay, but probably you need to protect the front, the aluminum lines on the front of the CMOS chip. Otherwise, they are etched much faster than the silicon which you would like to remove. So many tricks need to be invented. And so once you have answered these first two questions, then can you work on the third? That's assuming that you know quantitative properties. And you can start designing, making rough sketches, estimates. You can feed finite element programs with concrete designs. You can do parameter studies. And at the end, yeah, you maybe have a promising system that is worth developing. Yeah, you can go to your boss and say, well, in principle, I solved the problem. Now there is only the technological challenge to be addressed. Yeah, okay, that's usually the major challenge, but anyway, we have done a first step. Yeah. So in summary, we can look at it again here. We have some signals to be measured. We need to identify some transduction effects. We can identify some materials that are available in CMOS technology. We can dream up of a concrete example of a sensor structure, and then that can be optimized. And then this optimization will be guided by many parameters, sensitivity. How good is it measuring? Is it good enough? Does it measure ppm, concentration of volatile organic compounds? Can it resolve millikelvin in temperature changes under very small radiation powers? The stability, offset characteristic, cross sensitivities to other signals. In a Hall sensor, is the mechanical stress on the Hall sensor package, this beautifully hermetic package that lets the magnetic field go through. Is the mechanical stress acting on the chip doing something to the signal? And yes, it is. So there is a cross sensitivity. Temperature also goes through easily. Temperature goes through anything. It's just heat flows, and so does temperature change something? That's also cross sensitivity. So how do we then compensate these cross sensitivities by a proper sensor design with maybe additional elements that give us information to get rid of the undesired influence? Yeah. So now let's look at some CMOS technology. I will with the next slide start to explain you, a simple process flow of a CMOS technology, and then we'll see how CMOS structures are at least vertically elaborated. So CMOS combines NMOS and PMOS. We will work on PMOS and NMOS transistors in the next slides on the same substrate, and they are interlinked by metal lines of many layers. In the early technologies, when I was a postdoc, there were 2 metal lines. So that was okay. You can do many things with 2 metal lines. Now they have 10 metal lines in their chips to link locally, and then less locally, and then less locally, and big lines that bring in the power, and it's then distributed down to the very small components. I mean, here it says advanced technologies, critical dimensions, and I need to correct that. So this was indeed true in 2013. Now let me write some actual numbers. So in 2020, we had so-called 5 nanometer technologies. In 2023, TSMC is promising to produce 3 nanometer CMOS technologies. What does it mean? If we have such a, now I'm drawing a classical structure, classical field effect transistor. The critical dimension of a classical transistor. So I'm writing here source and drain, and here gate. And then maybe this is well, a little bit less defined. And then there is a length, the channel length, which I write here, L channel, that gives a measure of the size of the technology, because smaller channels reflect smaller sizes of overall devices, which reflect higher packing densities, and so this is kind of a one measure. It also means that the chip can be powered with lower voltages. The smaller this length is, the smaller the voltage that is needed to drive a current through. And so this length can be thought of a bit like this. But the modern transistors look different, actually. Yeah, they are often composed of substrate. Let me draw an insulator here, and then some silicon. Yeah, fin, for instance. Yeah, that has now some width of 3 nanometers. So it's a very, very thin slab of silicon material, and this is then surrounded by some gate structure that is insulated from the silicon by some ultra thin dielectric, maybe. And this central silicon fin is actually contacted in the front and back by some contacts. Yeah, so current flows in this device through the plane of the view graph, and the surrounding, almost surrounding gate is able to squeeze basically the carriers out or let them in, so that this beam of conducting material is actually either insulating or conducting. So these are some sketchy ideas of how these very advanced technologies look like, but it's more intricate than that. Yeah? And these transistors here, I mean, when you read 180 nanometers, 180 nanometer technology, yeah, that's how they were still constructed. Even 45 nanometer technologies had this kind of structure, but in the few nanometer technologies, this is no longer the case. And just to show you how this evolved, here is Wikipedia. I just looked up 3 nanometer before, and it produced me these numbers: 2023, 5 nanometers, 220, and then indeed in 2012 it was 22 nanometers. So we can look. When I was a postdoc working on my first CMOS designs, that was in 1992, around this period. So they were at 350 nanometer technologies, Intel and AMD and the other very advanced guys, Motorola. And we worked with 1 and 0.5 micrometer, 500 nanometer, or 1,000 nanometer, or 2,000 nanometer technology. So we did not use the top-notch technologies, too expensive. And still too expensive. And not necessary, actually, for MEMS design. So that's impressive to know that TSMC can do that, and that our iPhone chips and our computer CPUs will be more performing. But for the sensor systems, that's not necessary. So the most advanced sensor systems we did was in 180 nanometer technology, and that's already hugely dense. And going much below doesn't make much sense. Also in view of the fact it's impossible because the cost just increases exponentially. So to give you an idea, if we work on what was it? 45 micron structures from X-FAB, for so-called multi-process wafer run. No, actually, this was a wafer run for us, where we got 3 wafers guaranteed. We paid something like 25,000 euro. Okay, you need a research budget to pay for that, and some projects. And then going from there to 180 nanometers, rose the price to 80,000 euros. You can hardly imagine these numbers, but this is research money. So and you don't do that too often, because even a wealthy professor doesn't have the money, flowing freely like that. We're not the millionaires. We have to fight for our money, and then we use that money wisely. If we are lucky, we have some big projects that fund us, and then we can spend it, like BrainLink Tools, Excellence Cluster brought in a lot of money into the University of Freiburg, so we could use this advanced technology. So That's what I mean here. CMOS and MEMS, for MEMS usually uses lower resolution, and therefore we have older and therefore also more established, better established technologies. Yeah. In all those technologies, the basic technological steps are thin film growth and deposition, photolithography, etching, and doping. So I presume that you have had some basic technology training in the first year of your master curriculum. If not, that will come. Yeah, maybe if you're here in a very early semester. And even if that isn't the case, maybe you will grab intuitively what happens with the next slides. So these are the 4 basic ingredients of the cooking of a CMOS chip. I always compare technology with cooking. You have a recipe, you know what gestures to do, what mixtures to perform, how long to do things to achieve an objective, to make your perfect sauce, béarnaise, for instance. You need some tricks and some experience, and when you do it often enough, it runs stably and you can do it many times. And so it is with technology. You need tricks and knowledge and repetition and quality control. So what are we about to produce? We're about to produce wafers that contain as a tiny little structure this cross section. So the wafer is below, it's hundreds of micrometers thick, and we only see the top part, the top few micrometers. Also, it extends 200 millimeters horizontally. And we are seeing here maybe 10 micrometers or less, 5 micrometers. So it's only a tiny section, and it's only one vertical cross section. I'm aware that the ability of people to see 3D structures or cross sections is different, and it's also different across cultures, because one is trained according to certain ways how things are represented in one's environment. So you can imagine here this big wafer. Oh yeah, now it's a bit rotten here. Yeah. So this wafer has a thickness. So it has this diameter of 200 millimeter, for instance, or 106 inch or 4 inch if it's a very old wafer. And then we're basically cutting here vertically. So this is from the top. We're looking at a vertical cross section. And we're only looking at this top little piece of this vertical cross section of that wafer. And so what do we see? We see 2 semiconductor devices, namely a so-called P-channel, PMOS device. So you can increase the size a bit. It says PMOS on this side, and it says NMOS on that side. The PMOS, you see, by the fact that there are a source and a drain in this white silicon. And therefore the conductors are P carriers, the holes. And then there is an N region in between. And this N region in between is in a bigger magnification, separated from this reddish material, the gate. I can write gate here, and I can write source and drain here. From this gate, by a little thin oxide. So this is an insulator, and if I apply a voltage to the gate, no current goes into the silicon. But by an appropriate voltage of the gate, I can make it happen that charge carriers, holes, can creep along the surface underneath, the interface underneath the oxide, along here in a channel, in a very thin, few nanometer wide area from the source to the gate. And if I give the gate an inappropriate voltage, that creeping is not possible. There is no path, there is no channel anymore. So the gate switches on that channel or off. Yeah? Microelectronics has taught you that. But I just repeat it for the purpose of clarity. Yeah? So because this is an N region, there are no holes in here. Yeah? And you need to somehow generate the availability of holes in this area by creating a band bending towards the surface, which causes an inversion layer, and that inversion layer is the channel. And so when you have voltage applied between source and drain, then a current flows. Or when you apply a voltage to the source, then because there is this conductive region, then the voltage of the drain has to adapt to that if no current is allowed to flow. So this is a different view of this whole thing. And on the other side, we see this N-channel device, NMOS, N metal oxide semiconductor. Why metal oxide semiconductor? Again, the gate is considered as the metal, highly conductive. There is the oxide, and then here is the semiconductor. So metal oxide semiconductor, MOS. And N in this case, because the carriers are N carriers, electrons that need to flow from this N source to this N drain underneath the oxide, made possible by this appropriate gate voltage of this gate. Now, what else do you see? You see that the source and drain is somehow contacted with a metallization. So those black areas are metal structures. This might be aluminum or some other materials. Copper in more modern technologies, and you see here at least 3 levels of metallization. Actually, there is a contact metallization here. And then there is one that will really run over the chip. So it's a bit special here. I would probably call that actually. Well, actually here is a metallization. So it looks like a 3-metal process, but in a kind of special configuration. So probably specifically should only be called a 2-metal process. And then you have these other colorful materials in between. These are insulating materials. So insulators. This one too. So silicon oxides, sometimes doped silicon oxide, and maybe on top of silicon nitride. These are PECVD deposited or thermally oxidized materials, which insulate well, which insulate the metallic layers from each other. But of course, you need to go from one layer to the other at certain places, and this is symbolized by these pinkish structures that are the so-called vias. So this is called a via. It's the semiconductor jargon for interconnection through oxide layers, through insulators. It's a via. And so now let's see how this is elaborated. So one starts with a silicon wafer with nothing on top, just bare silicon. The silicon is some 100 silicon substrate, which means that the crystalline directions in the silicon wafer, so the cubic crystal directions are in such a way that one of the cubic axes is perpendicular to the wafer. And that means that the wafer has a certain arrangement of atoms on the surface, and this is what is usually taken for CMOS. This wafer is then cleaned, and then it is exposed to a thermal oxidation. This produces this little bluish oxide layer, a thin layer, which is also called the pad oxide in some, or stress relief oxide by the technologists, because it is actually, it's only a glue to the next layer that is elaborated on top, namely the silicon nitride. SiN means silicon nitride, and it is here explicited as a stoichiometric silicon 3N4. But it's an amorphous layer. It's not a crystalline layer. And this after this thermal oxidation that may be, 900 degrees for not too long a time, then the wafer goes into another furnace where some ammonia and some dichlorosilane flows through at high temperature, 900 degrees, and then that grows by decomposition of these gases and recombination of their constituents, there grows a silicon nitride layer. So we have grown a silicon oxide by consuming some silicon with oxygen, made a little oxide layer, and now we grow through this silicon nitride layer. And these are processes that are, as I said, at reasonably high temperatures. Who knows what LPCVD means? Chemical vapor deposition. Yeah, and what is LP? Thank you. Wonderful. Yeah, so it's not at atmospheric pressure. It's maybe a tenth of the pressure in some special furnaces. And then we see a yellowish layer that symbolizes the photoresist that is spun on top of that wafer over the entire surface, and then pre-baked, and then in the next step exposed to an optical pattern. So the mask is put on top, or adjusted on top, and then there is some exposure with some lamp with some appropriate light frequency or light wavelength, light energy, and that after some further processes, belonging to photolithography, so post-exposure bake and then etching of the photoresist. The photoresist is removed in certain areas. So I would, if I drew that here, I would say, okay, the photoresist has been removed here, and it has been removed here, and also here. And then with this remaining photoresist only now in place at these locations, we can also etch into the silicon nitride. That is going to be some rough process, either a dry etching process or maybe using phosphoric acid, but probably more a dry chemical process, some reactive ion etching process. And so that used a first transfer of a design, a first mask. Geometry has been transferred into the photoresist, and now from the photoresist, or thanks to the photoresist protection against this this reactive ion etching process, now has also been transferred into the silicon nitride. Then comes the next step. Local oxidation of silicon, or in the short jargon of technology is just local. This is the low-cost process, local oxidation silicon process, where now you see that of course, the photoresist is removed. We do not want to put the photoresist into a high temperature. It would just dissociate. So it's better to clean it off before. And then the silicon wafer with the pad oxide and this structured silicon nitride is put into a furnace, into an oxidation furnace, where a wet oxidation process is occurring, and not at 100 degrees. So that would be funny. Rather 1,000 degrees. And this wet oxidation process, basically a process where steam, H2O, is sent at high temperature over the wafer. It diffuses through the originally thin. So originally we had this thin oxide here on top of the silicon. It diffuses through this oxide, and then the oxygen is reacting with the silicon, and the hydrogen is released. And thereby we form additional silicon oxide molecules at the bottom of the silicon oxide. So silicon is consumed by being combined with oxygen, and this expanding layer then causes this blue layer to become thicker and thicker. Why it becomes thicker and thicker? Of course, silicon is consumed, and you can roughly say it, if I'm not mistaken, that I think from the surface to the bottom, about 45% of the thickness is going into the silicon wafer, and 55% is above. That's a rule of thumb. And I hope I'm saying it the correct way. It could also be the other way around, but my belly feeling tells me that this is correct. Or do you have another? Yeah. Okay. Have you heard that number before? Okay, then I'm glad. Yeah. So what happens here is that where the silicon was more exposed, namely here, it has grown thicker into silicon oxide. Where it was protected by the silicon nitride, nothing has happened. Because the silicon nitride did not let the water molecules through to the silicon to be reacting there. And so this is kind of the mask layer. Like photoresist is the mask layer against some removing process here. The silicon nitride is here now the mask layer against some growth of oxide. But you see also that this masking is not perfect. You see the silicon nitride has been lifted up somehow, because the water diffusion does not go only vertically through the oxide, it also goes horizontally. So if I draw that in more detail, so here we have our oxide, and here we have silicon nitride, and this is the silicon oxide, and down here we have the silicon. So the H2O molecules, of course, they will do their job down here to consume and let grow, but they also diffuse slightly underneath here. They diffuse everywhere, and it becomes just improbable for them to diffuse very far. But it means that there is also some growth occurring here, and then of course a lot here, which means that ultimately the silicon oxide layer will grow in this way, and the silicon nitride layer will have to give way to that growth. And this is a more realistic picture of what happens actually in this pretty sharp transition. And this structure actually is called the bird's beak, Vogelschnabel, in the technology jargon. Like a bird's head, and then there is a beak, very fine. So this has now elaborated a thick oxide, and you see where this thick oxide is used. You see here these thick oxide structures, thick insulator structures, that let you now run some metallizations over the silicon chip without contacting the silicon or having leakage currents and so on. This thick, the region with the thick thermal oxide is called the field. So this oxide is called the field oxide. It is not an oxide of field, it's an oxide of silicon, but it's the silicon oxide in the field, therefore we call it field oxide. Like the gate oxide is the oxide underneath the gate. There is vanadium oxide, iron oxide, and then there is gate oxide. And what element is gate? No, it's the oxide underneath the gate. Why wet? If there is wet oxidation, there must be another oxidation too. Dry. Is that also done with water? No. What is it done with? Oxygen, only oxygen. O2. Yeah. O2 is bigger than H2O. So H2O goes faster. So wet oxidation goes faster. If you need thin oxide, wet oxidation is not a good idea, as you know. Yeah? Okay. So now that we have the field defined, yeah, we know where transistors can be elaborated, namely in these two regions. And so one is going to be the NMOS and one is going to be the PMOS transistor. So what is happening next is that one of those areas is protected against ion implantation by an oxide, by a photoresist. And that photoresist now lets you do some ion implantation. So basically a directed injection of dopants, boron in this case, which are able to reach the silicon even through this little thin oxide that still remains. This pad oxide is still there. Yeah, the nitrate has been removed with some phosphoric acid, which does not etch silicon oxide, and now you have this this implantation reasonably close to the surface of these boron atoms, and of course you have also implantation of boron atoms, but they are stopped by the photoresist. It's blocked, and not any significant number reaches the silicon below. Yeah. Okay, then the same thing is done again with the other way. So here now we are injecting phosphorus, yes, to do some N-doping here. So here we have Nd, and here we have some Na, as it is called in the semiconductor physics jargon, some dopant, some donor concentration, here's some acceptor concentration. And from what I see here, actually, I have to conclude that the P substrate was very weakly doped. If it had already been heavily doped, then this additional doping wouldn't do any change. So it must be a very weakly doped silicon. It says P, but it's weakly P. So that when you inject some P, and even after that P has been distributed over a bigger thickness, what you have injected determines essentially the dopant concentration in this well region, this P well or this N well region. So what do these numbers mean? 10 to the 13 per square centimeters. That's the number of boron atoms that are deposited per area. And they don't stick there on the surface. They go inside, so they distribute over a thickness. But that thickness is experimentally well known by the knowledge of the implantation process. When you charge or when you shoot at a surface with 150 kilo electron volt boron atoms, you know that they go so and so deep on average, and will establish some profile, and you have that under control. But how many of those are there at this depth or distributed around that depth is given by this number 10 to the 13 per square centimeters. So after this has been done on both sides, you see that phosphorus has been implanted at higher energies. 300 kilo electron volts is kind of high voltage. This is not to be touched by the hand. So these machines are well protected. Ion implanters are big machines with lots of Faraday screening inside and high voltage generators inside to allow gases to be ionized and then to be accelerated and be shot and then be deflected and written line by line across the silicon wafer to deposit the right amount of boron. And the right amount of boron is measured by measuring the current of that beam. Current means numbers of charges, and when you know numbers of charges, you know also how many charges have been deposited per area, if you know how you do the scanning. Yeah, and then after this implantation, usually the surface is kind of destroyed. This means a lot of energy, so the crystalline surface is no longer perfect. So one does a so-called drive-in for a few hours at high temperature to, first of all, anneal the crystalline structure. So below it was still monocrystalline, and then this monocrystalline front just lets all the atoms arrange themselves on the perfect order of what is below, and then the perfect order just grows. And while this happens, the dopant atoms change places all the time, substitutionally, interstitially, and so on, and they diffuse deeper and deeper into the silicon. They redistribute over an area that may, or a depth that may be, so typically micrometers. Yeah, so 1 micron, 2 micrometers. And this is not so top-notch process. For Hall sensors, for instance, one uses roughly 4 micrometer deep end wells. So 4 could also be 4. Right. What else did I want to say here? Implant damage, yes. So that's a long process. These diffusion processes are not very efficient. So one has to either go very high in temperature or very long in time. Diffusion constant, D times T, is the parameter that tells you how far you go. The typical diffusion length, L, is so of the order of square root of dt. So if you would like to go 4 times as deep, no, 2 times as deep, you need to diffuse 4 times as long. You need to go 10 times as deep, then you need to diffuse 100 times as long. Okay, now come the next steps. So these wells are, if we go back to the original structure, oh, what has happened? No, so these wells, now we have basically produced these containers of the transistors with well-defined doping, low enough so that we can easily generate these differently doped sources and drains. So the N well receives the P source and P drain diffusions, and vice versa for the P well device. So that the region under the gate has the N well doping. So that you have this PNP structure in the left that can be switched on by the field effect. So what now comes next is actually that this doping is not good enough yet at the surface. In order for the transistor to switch on at a well-defined voltage, a threshold voltage, you need to adjust the doping at the surface where the channel will be. And that is the so-called channel implant, or the threshold implant, threshold voltage implant of the NMOS device. So on the left with the P well, we do some additional boron deposition to make it slightly more P doped. Now you see that the number of charges, or the number of boron atoms, is lower, because we will not want them to go very deep. And we are not implanting them at a very high voltage. We want them to remain more close to the surface. And that is happening at these lower energies. And then after that, we do the same for the P channel devices on the left, where we protect again the right-hand side with photoresist, and do some arsenic implant, again 10 to the 12 at 100 kilovolt. Remember that this was 300 kilovolt before, deep, to go really deep with the well, and now we are doing something quite shallow. And also note that now we already have used 5 masks, back and forth. Well, actually, we kind of use the same mask again, for this left and right protection. This has happened now several times. So we did not use different designs maybe, but we have done lithography many times. And repeating technologies over and over again increases always the chance to do something wrong. The overall rate of failure is a product of individual rates of failure. So the more complicated technologies are, the better controlled the individual steps must be, so that at the end something useful comes out. If you lose at every step 1% and you do 100 steps, 0.99 to the power of 100 is a very small number. It's more than 0, but it may not be enough to earn money. And so if you do 100 steps with 99.99% of survival at every step, maybe then you lose only 1% at the end, and then you're doing good business. So that's to be kept in mind. So now the next thing is that actually this photoresist is, of course, again removed. And what we have now is this field oxide. We have this thin pad oxide from all at the beginning. We have the wells, and we have these threshold implants in place. So in principle, we can now construct transistors that will work. So the next step is to deposit this reddish layer here. That is polysilicon. It's deposited again at low pressure by chemical vapor deposition of some silane or mono, bi, or trichloro or tetrachlorosilane. There are different processes at this reasonably low temperature, and at that temperature, the silicon that is now dissociating from that chemical gases compound settles and crystallizes in microcrystalline structure, and then those structures grow. And so at the end, you have some polycrystalline structure that constitute your gate material. And this gate material covers the whole wafer, of course, because the wafer is in the oven, the gas goes everywhere, and the wafer is again covered. So this was the first deposition step. So far we had growth steps. No, actually the silicon nitride of this low-cost process was also deposited. But the oxides have all been grown. They were not deposited, they were grown from the silicon. And here we have, now I correct myself, the second real deposition step of this gate material, and the thickness of this gate. Maybe I should talk about thicknesses also here. This thickness is, well, maybe 0.3 micrometer, 300 nanometers. And it's highly doped, as it says here, with phosphorus, P, so phosphorus doped, to make it highly conductive. And the sheet resistance is reasonable, 25 ohm. That's what I know also from fabs with processes I've used. Polysilicon gates have very often this this sheet resistance. Who does not know what a sheet, or let's say, who knows what a sheet resistance is? Have you heard that concept before? Yeah, very shy, shaking. You have not. Yeah, who has heard it? No, never heard. Okay, good. So let me talk about sheet resistance. When you have a thin conducting film, you have some material with some resistivity. That film, if you produce, let's say, a little resistor from this material, this thin material that has some thickness. Now let me draw that here. Thickness T. You can easily calculate the resistance of the structure. Let's say when a current flows in this direction. Yeah. So let's assume the width to be W and the length to be L. Then we can calculate the resistance as resistivity times length divided by width by area. Okay. And then area is, of course, width times thickness. Cross-sectional area, that means. The black cross-section. Yeah. This cross-section is W times T. Yeah. So now imagine that you write this a bit differently. Yeah. I can say, okay, we have a resistor that is n times as long as wide. So L is n times the width. So if n is large, it's going to be a long resistor. If n is short, it's going to be a short resistor. So if I substitute that here, what do I get? The resistance is equal to rho times L over, no. Let me correct that. N times L, no, W over W times T. So if I simplify that, I obtain rho times 1 over T times N. So all I need to know the resistance of this object is the number of what? The number of squares that constitute this resistor. Because this N is the number of widths, and if I have a section of length W, the length L is going to be N times this length of the square. So by drawing this a bit more explicitly, if I say, okay, now I have n squares. I know from the width of my resistor, I know, and if I have n, I know immediately the length. Length is n times W. So this is another way of viewing this. So if I know the number of squares that constitute my line, and if I know this parameter, rho over thickness, only thickness, no other geometry, then I know the resistance. And so this particular construction is called the square resistance or sheet resistance. You only need to know the resistivity and the thickness of the material. Then the design only boils down to the aspect ratio of the line, not to the absolute dimension. So a line that is 1 micron wide and 100 long has the same resistance as one that is 10 micron wide and 1 millimeter long. There's 100 squares in both of them. That's why the square resistance is very useful. So the square resistance or sheet resistance of polysilicon is 25 ohms. And implantation to saturation means that not more phosphorus goes in. That means about 10 to the 21 per cubic centimeter of phosphorus doped into that polysilicon. So about 1% of the atoms are substituted by phosphorus. It's very high. If you put in more, then the polysilicon will react with the phosphorus, and then you'll have another material, but you want silicon. So don't put more in. Okay, what time is it? 3:45. Do you allow me to continue a little bit because we started a bit late because of this turmoil, or do you have other deadlines now? Yeah, if you say that you have to run to the next lecture, then of course I will let you run. Yeah. Okay, then we will stop now and then we'll resume this story on next Monday at 4 o'clock. Yeah, so thank you very much for your attention and I'm looking forward. I don't think there will be some exercises. I have to look if I have some material, whether you have something to work on until next Monday. And if not, then you will not receive a message and we'll just continue with the lecture next Monday. Yeah? Bye-bye.